armature winding is responsible for, your output power. However, in certain cases, to compensate flux, if your field is not capable enough to produce rated flux, in such cases, armature winding can produce magnetizing or demagnetizing component. Right? If your flux is over-modulated in your machine, if your machine is saturated, in that case, armature winding can be able to produce demagnetizing component of MMF. Otherwise, if your machine is under-excited, right, in such cases, your armature winding can magnetize the core of the machines. Okay, so I hope you are aware with those concepts. So we will not go in deep of those, and we will focus more on the problems. So uh, let us start with a gate problem which was asked in gate 2023. Right, so this was asked in gate 2023. So kindly read the problem very carefully, and here we have to find out the excitation voltage. So what do you mean by excitation voltage? First, we should be clear about what are the objective of this problem, okay, and how to calculate excitation EMF or excitation voltage.
E, sir.
Yeah, sorry, could you please repeat?
E. You have to find E.
E, EF, right? Field. That excitation voltage that will be induced because of the current flows in the field winding, right? So we have to find the EF. Our objective is clear that we have to find the EF. So how can we find that? Because we have been given with a static stability limit of 2.5 per unit. So the question is dealing with per unit components, and here synchronous impedance is also given, right? So uh, I think you might know the expression of a static stability limit if there is no resistance. If there has been only inductances, then you can directly put Vt into EF by XS sine delta, right? But here we cannot do that. And hence they try to check that we just not memorize the concept or formulae. We also should know the basic concept behind it. Okay. So yeah. Then other thing is that we can find out the, you know, we if you there are two approaches. Okay. What are the first approach is that, you by heart all the expressions of, real power, reactive power, input, output, real and reactive power, developed input and output, real and reactive power in case of motor, and in case of generator, you remember all the developed input and output power, and as well as, output power at the shaft, reactive power as well. So I think that would not be an easy approach to, remember all the expressions and apply immediately in the exam. So many times it's recommendable approach is that you just be aware with the basics, right? And you just proceed with that, and if you are able to solve with basic concepts. So how to go ahead with basic, if you can give some, idea about it. So a static stability limit here we should deal with uh, every time. If it is motor, we cannot calculate output power directly without losses are given. So we have two things: either we can compute input power and developed power, but a stability limit is generally decided by our developed power, and that developed power, how much it is being developed, right? It should not violate the limit. So the peak developed power will be 2.5 per unit. So 2.5 times of your rated power that can be developed in the motor. Generally, we do not operate at that level, but that is the condition is given in the problem. So what is the expression of developed power in case of motor, synchronous motor? So let's suppose in a machine you are providing an input, and since this machine is a motor, it will have some copper losses, right? Afterward, there will be some developed power at this level, okay? And this developed power will be reflected to your shaft after certain losses in mechanical. Since it is an electrical to mechanical conversion device, mechanical or rotational losses, then you will have shaft power. So how much will be developed here, that will be responsible in deciding the static stability limit of the machine. Okay, fine. So let us draw an equivalent circuit as well. So you have given your terminal voltage as a supply, right? You will have certain armature resistance and inductance, winding inductance, synchronous reactance, right? And armature resistance. And here you will have induced EMF, right? And armature current will flow in the circuit. Till now, I hope it is fine, right? And this is the stage where you can calculate input power, right? So S input, we are dealing in terms of apparent power because both type of power will flow in the circuit, real as well as reactive. So it is better always deal in terms of apparent power. So whenever you need to find out the real power, you can do so. Or in case of reactive power, you can also derive that, right? So input power will be VT conjugate, right? But we are concerned with the developed power. So we can also write as developed power is equal to EF IA conjugate. Is it fine? If there is no doubt, then let us move ahead with developed apparent power. Okay. So we have to find the EF, right? We have to find the EF, and S developed, you can always break it as P developed plus J Q developed, right? And we are given with this value, this limit. Okay. So this limit is 2.5 per unit. Now, I hope you are following. So EF will be one unknown component which we have to find. Now, what will be the expression of IA? IA from this circuit, you can write VT minus EF by RA plus JXS, right? So simple KVL, IA, let me write it, VT minus EF by RA plus JXS. Now, I just need to plug in these values here so that we will be able to find the S developed. EF is fine, right? Now IA is VT minus EF, but we also have to, take care of delta, right? So if you are assuming VT as a reference phasor, VT at angle 0, then EF will lag by your load angle. I hope you are aware with this concept, right? Are you aware with this in case of motor?
Yes, sir.
Okay, great. So I can easily write it in this manner. Z angle theta, since it is a lagging. Now, here also we should mention minus delta conjugate EF minus delta Vt by Zs. What will be angle of this component?
Minus theta.
Minus theta, yes. Minus EF by Zs angle minus delta minus theta, right? And conjugate. So if you further simplify it, EF angle minus delta and conjugate of minus angle will be plus, right? So Pt by Zs angle theta minus EF by Zs angle delta plus theta. I hope you did not find any difficulty in manipulating this expression. Now we have to simply multiply it. So it will be EF Vt by Zs angle theta minus delta minus EF square by Zs. Yeah, any question? Delta plus theta. Okay, till now it is fine. Now, do not forget that we were deriving these expressions to find out the real power so that we can evaluate the static stability limit. Sorry, steady state stability limit, right? So the power developed will be cosine of these angles, right? If you take cosine of these angles, that will give you the real power. If you take sine of these angles, it will give you reactive power. So EAVT by Zs cos theta minus delta minus EF square by Zs cos delta plus theta. So this is the expression of the developed power. But since we have to evaluate the steady state stability limit of the motor, okay, it means that read the question once more. What does it mean? Since you have to find out the static stability limit that is given 2.5 per unit, it means at that value the developed power will be maximum. And what will be the condition of the maximum developed power? That you have to evaluate from this expression. So when this expression will give you the maximum power? When this expression is maximum, right? Or you can do one thing, you can differentiate it and find the local maxima point, and you can evaluate from this that way as well. But it's quite obvious that if you have maximized this component, then at that angle, if and to maximize this component, you have to maximize this component, cosine component, and cosine will be maximum when it is 1. And when it is 1, when theta minus delta is 0, right? And at this condition, delta will be equal to theta. I hope you did not find any difficulty in this.
Sir,
Yes, go ahead.
this delta will get cancelled in second line
In second line, delta will get cancelled
because
here.
EF has minus delta angle.
Yes,
This EF, outer EF, when
this one,
you
this one,
no
this
sir,
one.
in
S developed, sir. In S developed.
Sorry, I am indicating here A, B, C. Which expression?
A, sir.
A. In A, it should get cancelled. Okay, let me see. Okay, minus. Yes. Thanks a lot. It will be cancelled. Thanks a lot. This minus delta and this plus delta will be cancelled because it is minus, it is plus. So only theta will be present. Thanks a lot for pointing that out. Okay. So here now again, what will be the value of theta that will be equal to delta at when this cosine will be maximum? So we can say that a static stability limit will be how much? EF et by Zs cos theta minus delta. We have already done that, minus EF square by Zs. So let me cos theta. Okay. Now we know Vt in terms of per unit. Okay, it is 1 per unit, right? And Zs is given. Zs is given how much? Zs is given 0.1 plus zero point 0.3. So please calculate the magnitude of it. I guess it will be, please calculate it and let me know. Angle theta as well. Okay. So theta will be tan inverse zero point 0.3 by zero point 0.1. So it will be 3. And 3 comes at, I can't remember that, but please find it out. So the unknown term is EF, right? And the static stability limit is given as 2.5 per unit. So 2.5 is equal to EF. ZS, did you guys calculate?
sir,
Uh-huh.
magnitude is 0.31,
0.31 and theta S?
71.
Theta S is 71. Sorry, theta, not theta S. So, okay, it is fine. Now, again, minus EF square by ZS is 0.31 and cos 71. So, now it is just a quadratic equation. Okay, so EF square cos 71 by cos 71 by 0.31, it will be 1.05, I guess, minus EF by 0.31 minus 3.225 EF plus 2.5 is equal to 0. So this is the quadratic equation, and from this expression you can calculate the value of excitation EMF at the condition of a static stability limit. Okay, and if I just calculate it, let me calculate it. Are you guys able to calculate it?
Yes, sir, we are calculating.
Okay, okay.
Sir, one value is EF is 1.53
Mm-hmm. Five
minus J 0.15,
minus J 0.15. Okay.
and
And
another
other one?
is conjugate of it. A conjugate of it.
Okay, conjugate of it. Okay, so if you just take the, mod, that will be the magnitude of your excitation EMF. So 1.53 square plus 0.15 square. So it will be 1.54 approximately. Sorry. And the load angle from this expression also you can calculate, right? Since EF will have magnitude and minus delta, so delta also you can calculate from this approach. Okay. So any doubt in this overall question?
Hmm. Sir, please summarize it because I had joined late.
Okay, so see, uh, in this question, the motor has a static stability limit of 2.5 per unit. Okay, and its synchronous impedance is also given in per unit. So we had to calculate the excitation voltage, that is EF. Okay, so a static stability limit when synchronous impedance comes in picture with with resistance. In that case, you have to go through the entire expression of developed power, and you have to find the maximum developed power. Okay, so many times what we do, we try to remember this expression. That's another way. There is other way that you solve such problems so many times that automatically you remember. Otherwise, if you try to forcefully remember it, it's most certainly that you will forget in the exam because it is very confusing. Motor, generator, reactive, real, developed, input, output. So there are many expressions. So what I suggested that go through the basic concept of what is the apparent power at the developed end and at input end, because output end will have developed minus mechanical losses. Similarly, in generator you will have developed as well as output. Input you have to calculate from the mechanical and rotational losses. Okay, so with this approach we moved ahead with developed power is equal to developed apparent power is equal to developed real power plus reactive power, and the maximum value of developed power was given equal to 2.5 per unit. And we have drawn an equivalent circuit of the synchronous motor. Okay, where Vt will be at the input node and Ef will be at the developed node, where at this node, right, where the power will be developed. And in between, armature resistance and synchronous reactance will be placed, and accordingly I think it is just an AC equivalent circuit which you must have studied in you know earlier courses. And from that, using your AC analysis and using uh, accurate phasor way, just now you guys seen, right, I committed a mistake in phasor, and it is very common here that there are so many angles that you might end up doing certain silly mistakes, and that will end up you losing your 2 marks or so. So that you have to very carefully think in the exam, such, and you verify it once or twice so that you do not make such mistake, and you move ahead. And as we ended up with the expression of developed power, we found out the condition when we will get the maximum value of the developed power, that ended up with delta is equal to theta. And since impedance was given, so we calculated theta, and EF we had to find out, and VT we considered as 1 per unit, because any one, either VT or EF, you can consider as reference, and you have to solve accordingly. And we ended up with this quadratic equation, and this equation gave us two conjugate solutions, and we ended up with this value. So I hope it is clear now.
Okay, sir. We are using here all per unit value.
All per unit values, because questions data were provided in per unit values.
Okay.
Okay, so it's better if you deal in the same terms. And anyway, here no ratings and all are given, so you cannot convert into actual values. So you have to go ahead with only per unit. There is no alternative in this particular problem.
Yes, sir. Sir, how you did assume that VT is 1 per unit?
See, generally, if you are dealing with such, you could have assumed EF also as 1 per unit. You have to take any one as a reference, right? In synchronous machine, you if you are operating at, and another reason is if you are operating at a static stability limit, it means there must be rated value of voltage should be applied at the input, so that with rated value of voltage you can go ahead of the rating of the machine. Since the rating of the machine, you can infer from this static stability limit is 2.5 times of the rating of the machine. So it is one thing, and other thing is that when you are solving such problems of synchronous machines in in per unit sense, in transformer also we did same, right? We considered VT as 1 per unit in voltage regulation, right? So we have to consider 1 per unit, and it's up to you. You could consider of EF as 1 per unit, one angle zero you could consider EF, and now VT you have to consider VT angle plus delta. Right? In case of motor, in case of generator, it will be inverse. Is it fine?
Yes, sir.
Okay, great. So let us solve one more problem, which was asked in GATE 2022. Okay, so read this problem very carefully. And again, here we have to find out the value of excitation EMF, phase value of excitation EMF. And here, synchronous motor, a star connected three phase ratings are given. So you can deal in terms of per unit as well as actual values. It's completely up to you. And here, one very convenient thing they have provided, that we have to deal with only synchronous reactance. So whenever resistance comes in the picture, it gets a bit lengthy. So negligible armature resistance they have already mentioned. The shaft load, which means output load. Just in the previous problem, we have specified the power flow diagram. So you might be able to imagine that shaft power is at the output, right? 10 kilowatt with zero point 0.8 power factor leading. Now, the loss in the motor is provided at 2 kilowatt. Okay. EF per phase we have to find out. So what should be our approach for this particular problem? Again, it's convenient. It will be very convenient for you if you draw an equivalent circuit first thing. Okay. If you draw the equivalent circuit, the question will become very simple for you. Now it's just an simple inductor circuit with AC, right? And yeah, VT angle 0 if you consider, then
Sir,
EF
it is a
angle
per phase equivalent circuit.
per phase equivalent circuit. Yeah.
Okay.
So since we are given with motor, right? So if we are given with motor, we can calculate from the equations two things, either input power or developed power. For output power, we need to know the rotational and mechanical losses particularly, not all the losses. And since in this problem, particular mechanical loss is not provided, so we left out with only two options, developed power and input power. Developed power we have to discard because we don't know the particular mechanical and rotational losses. So we have to end up with input power, right? So input power is equal to Vt angle 0, Ia, whatever be angle phi, right? And yeah, three times you have to do. Now, I hope it is fine. We are not going with apparent power. It's better that you move ahead with apparent power, but since this is very simple, circuit, so you can move ahead with this thing, right? Or it will be expression of apparent input power only. But if you are given with such a simple circuit, you can just, right, see VTIA cos phi, sorry, cos phi. Any doubt in this step? I can clarify it once more. Okay. If you are taking only phase values of voltage current, you can multiply with 3. If you are dealing with line value of voltage and current, you can multiply with root 3. Okay.
Sir, here we don't do that A conjugate, sir.
VA conjugate only we have done. If you let us do that way. Okay. Let us move ahead with that way. VT angle 0, fine. IA conjugate. Okay. Now VT angle 0, IA is VT angle 0 minus EF minus delta divided by JXS.
Sir, EF has lagging power factor in case of motor.
Yeah, yeah. Not that is not power factor. Exact term is load angle or torque angle. Okay, but it will be lagging, yes, in case of motor. Because whenever power flow from higher end to lower end, the higher end has the highest load angle compared to the lower end, the side of sink compared to the side of source. So if you do it, VT angle 0 into um, VT by JXS. So J we can write it as minus 90, right? Minus EF by XS minus delta minus 90. And now we will take the conjugate of both the terms. VT angle 0, VT by XS, angle 90 degree positive minus EF by XS 90 plus delta. I hope till now this is fine, right? And if you are plugging in all the line values only, then you do not need to worry about the factor of 3 or root 3. Okay. But when in the case of you will plug in only phase values, then you have to multiply with it with 3 in the end, right? So at the end of every problem, just verify whether you have taken the line values or phase values. Okay. So now it's time to clubbing in both the terms. Vt square by xs angle 90 minus VT by xs 90 plus delta. Okay, so this will be your input apparent power. I hope it is fine till now. Now we want to compute input real power. You just have to take the cosine of both the components, and it will be Vt square by xs cos 90 minus VT by xs cos 90 plus delta. So we will end up with this is 0 and this will be minus sine delta. So we will end up with VTEF by XS sine delta, which is very famous expression, right? When only inductor is there, doesn't matter whether it is a generator or motor, you can straight away write it is input power is equal to VTEF by XS sine delta.
Sir,
Now,
VT is line voltage or phase voltage?
here VT and EF will be line voltages only because we haven't used any factor of 3. Now, if you want to use the phase values, then you have to multiply it with the factor of 3. Okay.
Yes, sir.
Yeah. So what we were finding, yeah. So we were finding EF, right? In the problem, it was given magnitude of per phase excitation EMF of the motor. And is delta given? I don't think delta is given, but we are given with power factor. So what to do now? We have our expression. In our expression, we have known components as input power is nothing but 12 kilowatt, that is 10 plus losses, right? Vt, we know, Vt will be 400 volt. Xs, we know, Xs is 1 ohm per phase. But we don't know EF and sine delta. We ended up finding out 2 unknowns. And now what to do? How to find EF or delta? If you find out both, and you have to find out the sine delta, right? Then only you can find EF from this expression. Otherwise, you could find out EF from any other expression. So do we have any other expression? So yes, we have, right? Did you guess which expression we are gonna use from this KVL? Did you get the idea? Can you apply KVL?
Equal to IA JXS plus EF
Exactly,
rectangle.
exactly. Just simply you have to apply KVL, right? So VT will be equal to EF plus or minus EF plus JIA XS. Okay. Now it is not as simple as it is looking, right? So VT angle 0, we have to consider EF, we don't know, plus J, if you want to eliminate this J, excess, we know excess is given as 1 ohm, right? 1 ohm into IA, we don't know yet IA, but we know power factor is 0.8 leading, that will be plus 36.86. And J is multiplication, so we can add 90 degrees, right? So from this KVL expression, and VT also we know, right? VT is given as 400. So when you are applying, you just try to maintain the phase value. Yeah. So now this expression will give you the value of EF given that you calculate the IA. And IA should be the first thing if you are given the motor ratings in the problem. So since we are given the rating of 50 kVA, right, and 400 volts, so and it is a star connected, so IA you can directly calculate root 3 into into you know mm, root 3 400 volt. So this is approach, right? But the question is that we have learned to find out the armature current. By default, we should calculate from this approach. But will this value, what this expression will provide, be eligible in for that particular expression, for that particular condition? I just saw the rating 50 kVA, 400 volt, three phase star connected, and I just calculated that value. But it is the rated armature current. And this current, this particular motor at this particular instant might might not be operating at rated condition. And the condition is also given that what is given as condition that input power is the rating of the machine. So input power is 12 kilowatt, and if you find the input kVA, that will be 12 kilowatt divided by zero point 0.8. So 2, 3, 15 kilowatt, 50 kVA, okay, at zero point 0.8 leading. And so this is the condition where your motor is operating in this particular problem. So now armature current you have to calculate according to this condition. And if you calculate armature current now, IA will be 15 kVA divided by root 3 into 400. That will be how much it will give? 15,000 divided by root 3.
21.650.
How much? Could you please repeat?
21.650.
21.65 amps it will provide you. Okay. So now we have found out the armature current at that particular condition. We can just plug in here, right? 400 by root 3 will be 231 minus IA. We have found out 21.65 angle 90 plus 36, 126.86. So whatever you will calculate, whatever your answer will be, that will be the magnitude of phase voltage of excitation EMF. So can you calculate this particular phasor or complex value? Since in the problem you are given to find out the magnitude only, so it's fine if you only calculate magnitude to save your time. But again, you have to break this component into two, real as well as imaginary.
Sir, here can we directly subtract the magnitude or we need to change the rectangular form, sir?
Yeah, you have to change into rectangular format, right? Because it is a complex and it is, real. So first you have to bring it into real as well as imaginary. So you should have two solid component. One should be entirely real and other should be entirely imaginary. Then you find the equivalent of those, and then that will give you the magnitude.
Okay, sir.
Sir, I am getting magnitude 243.59.
243.59. Okay. So did you calculate angle as well or only magnitude?
Sir, 1 minute. Sir, angle is 175.92.
175.92. That is positive or negative?
Sir, positive.
In any case, it is not a valid angle. You know, your EF will not lead from VT in case of motor, and so that by such a huge amount. It is approximately anti-phasor, right? So what will it do? It will completely demagnetize the machine. So I don't think it should be. Uh, but anyway, you just calculate it, and uh, I think the magnitude should be fine. But since magnitude is
17.32, sir.
17.32, that is positive or negative?
80, sir.
Negative. That's seems reasonable. 17.3, and magnitude is same.
Yes, sir.
Okay, great. So yeah, so this, as per you, this is the answer for this particular problem.
Sir, how did you calculate IA? Please
I
explain.
IA we calculated from the whatever the condition we are given, right? So we are given that 10 kilowatt of output power as well as losses we were given. So we converted to input power because you can calculate armature current either from the developed power or input power. But you do not have access to the developed power since you don't know the rotational losses in the machine. So you have to go through the input power, right? So we went to input power and finally we calculated the armature current that is equal to apparent power divided by voltage. Okay. So
This is a
apparent
line
power,
current, IA.
line. This is line current as well as phase current. Both will be equal in a star connected, right?
Okay, star connected now.
Hmm.
Then angle I of IA.
Angle of IA is given 0.8 leading power factor. No.
Yes, sir.
Yeah.
Sir, please share this PDF.
Definitely. I will share.
through driving, sir.
Uh, uh, yeah, in Drive you are getting all the week's video.
Videos will get, sir, but PDF is not available, sir.
Okay, so again, I will upload on my YouTube, and in the description box, I will provide the PDF of this lecture. Okay, so I hope you are aware with the channel name.
Yes, sir.
Yeah, so that is JDS at the rate IITB. You just search and you will end up there. So now we will, clarify the difference of angles in machine and how does power flow with the difference of load angles. This problem was asked in particularly GATE 2021. So read the problem very carefully and please let me know. So it is an alternator, right? So now you have to think in terms of generator with internal voltage of one angle delta one. So one angle delta one is your internal voltage and synchronous reactance is given 0.4 per unit. What do you mean by internal voltage, by the way? Internal voltage is nothing but your excitation EMF, right? So basically power flow will be reversed in the case of
Answer is
generator.
60 degrees, sir.
Answer is how much? 50 degree, 60.
60 degrees, sir.
Yes, 60 degree. Yes, that's correct. So now you have to lead me in solving this problem, right? So how should I approach for this problem? What do you mean by internal voltage? I just clarified that it is just your EF is one angle delta one per unit. Excess is given 0.4 per unit. It is connected by a transmission line of 0.1 per unit to a synchronous motor having a synchronous reactance of 0.35 per unit. Okay, and its internal voltage is 0.85 unit. So there are a lot of data.
And sir, there is two synchronous machine.
Yeah, two synchronous machines connected. So if the real power supplied by the alternator is 0.866 per unit, then you have to find out the difference between delta 1 and delta 2. Okay. 0.866. It is equal to root 3 by 2, right? So what will be the angle of delta 1 minus delta 2? So again, I can't emphasize enough. When you are dealing with synchronous machine, you have to draw the equivalent circuit. So whoever solved this problem and told me the correct answer, you have to lead me. What will be the connection look like? So am I drawing correct?
Yes, sir.
Yeah, so it will be EF that let us write in terms of numbers. So one angle delta one, right? What will be the value of it? I think J.4. This is your synchronous reactance of generator. This is synchronous reactance of line, not synchronous
Transmit
transmission line, and this is synchronous.
motor, synchronous motor.
Yes, so that is 0.35, and it is also given 0.85 angle delta 2. Okay, now since all the inductances are provided in the circuit, you can straight away use that expression of real power, which is V1 V2. And this expression is very famous in power system as well. So if you go in power system, you can find out many times. Your transmission lines are generally indicated by an inductor. Okay, did that expression make sense to you?
Sir,
Hmm. Yes, go ahead.
Sir,
Go ahead. Yeah, Deepak, you are trying to say something.
sir, this
sir, we go
expression
to
Hmm. This expression what?
is coming from where?
Okay, coming from where? So in last case, let me go back there. Did I derive for this particular just previous problem? We ended up with VT EF by X sine delta, right?
Yes, sir.
Yeah. So VT was nothing but VT angle delta. EF was EF angle zero. If EF instead of VT angle delta and EF angle zero, if we replace it with V1 angle delta 1 and EF angle delta 2, then what would have been the expression of power? V1 EF by XS sine delta 1 minus delta 2. Or what you could do after the lecture, you just go back and derive from this apparent power expression for this particular circuit. Okay, for this particular circuit, you derive it. Okay, power is equal to whatever. Here we are asked about real power supplied, means input power. So input power at this node, one angle delta 1 will be your voltage, and current conjugate, that will be your apparent power. And from that apparent power, you can calculate the real power, right? And you will end up with this particular expression, because one term will be cancelled out because of cos 90, since it is an inductor. Just like here, this component will be cancelled out, and you will end up with this particular expression. So are you able to relate at least the analogy between
Sir,
those two circuits? Yeah. Okay. So we just need to find out the difference between this angle. It means if we calculate the sine delta 1 minus delta 2, we will end up with having those values. So power is root 3 by 2. P1 is 1. Okay. V2 is 0.85. Xs will be summation of all three inductances. So zero point 0.4 plus zero point 0.1, that will be 0.5, plus 0.35, that will be 0.85. Sine delta 1 minus delta 2. Okay, now we can easily cancel those out. So you will end up with sine delta 1 minus delta 2 is equal to root 3 by 2. And root 3 by 2 is the value that comes at what angle? 60 degree, right? So it will be your answer. Wasn't it easy?
yes, sir.
Yeah. So such kind of problems you need to practice. Yeah, just based on the basis of equivalent circuit and apparent power. So you must be very well versed with SE analysis, sinusoidal steady state analysis chapter that you study in circuit theory, right? So then it will be very easy for you. So I guess
Sir.
that's all. Yeah, go ahead, please.
No, sir. I am saying yes, sir.
Okay, okay. So I think we should wind up the session here. So any final doubt we can take, otherwise we will meet again on next Friday.
sir, could you please make on a torque-based problem, sir? Torque.
Torque based problem. Okay, so okay, anyway, power, if you divide it by speed, it will give you torque, but I will note it down. So I will choose those particular problems in which torque will come. Okay, so in the next session we will deal with that, and also we will try to see some questions based on parallel connections and loop in the frequency of the machine, right? So that is very popular topic which gate always ask uh, in parallel operation, how much a loop occurs in the frequency at the loaded condition from the no load. That we will try to see and cover in the next lecture.
Sir, could you please take a 20-minute for basic of synchronous machine? Because sir, I am studying in 5th sem, so now I am not doing synchronous machine.
Okay, so you have to let me know which specific topic you want, right? Because I cannot start from the scratch, so you have to let me know that.
Sir, just this equivalent circuit of
Okay,
this.
so you did not get the equivalent circuit. You just go through the lecture once, how I have drawn this equivalent circuit. Because see, all of the synchronous machines can be drawn with just two components, one armature resistance and other is synchronous impedance or synchronous reactance, right? So I think from solving the questions you will get idea. Otherwise, if you want to get very basic, uh, you just follow one of the lectures by that professor. What is yeah. Which course you are attending of machine?
So now DC machine course I am attending, but in
By
upcoming days, synchronous machine will go start in
but
upcoming
its lecture
days.
will be already uploaded on the YouTube. So uh, that course is by
Tapas sir.
Tapas. Yeah, so by Professor Tapas, you can attend that. You can see those lectures.
Electrical machine when they are tolding only about DC machine.
Yeah, in this particular module, but if you search on YouTube, synchronous machines by Professor Tapas Bhattacharya, I think you will get those lectures. You just see once. If it is not there, then we will try to cover some concepts, right? Okay, we will try to clarify basics as much as possible and that should be enough to solve any problems, and that should be enough for basic understanding as well. But since we are limited with 1 hour of time, so we can do so much only. But yeah,
Sir,
I will
someone
try
is
to take
asking.
a some big so that and that will cover entire arena of that particular topic.
Sure, sir.
Okay then. See you on next week. Thanks very much for joining the session. Bye.